with the trend first. Let me open up my stuff. Oh yeah, okay, cool. So do you wanna run me through what you think about the trend, what the question says?
Which one?
The one with the table and the trends.
Ah, okay. Yeah.
Yeah, you alright?
Yeah. I already got it open.
Did you scribble some notes on it or something?
Kind of. Yeah, sure.
Okay, cool. Just run me through your idea.
For 4A part 1,
Okay.
ionization energy, it's the energy to remove one mole of electrons. So if the ionization decreases down the group, that means it must be easier to remove the valence electrons down the group. So nucleus holds the valence electron less strongly, and then which means it must be further from the nucleus, right?
Okay. Anything else? Anything else you want to add?
Ionization energy decreases because atomic radius increases down the group also.
Okay, cool. I mean, you're more than welcome to add anything or just say it's enough. It's fine. I mean, I don't care about the marks. It's more about how you think. Okay, how about the second one? Have you learned about electron affinity yet?
Yeah, already.
Okay. So what do you understand by electron affinity?
That'll be changed by adding 1 mole of electrons to 1 mole of gaseous atom to form 1 mole of gaseous anion.
Okay. So what do you think about the trend there? Why is that?
I said that fluorine has lower activation. Energy electron affinity. He said that even though fluorine is more smaller than chlorine, chlorine has a higher effective nuclear charge.
Okay. Well, I mean, the fact that it's smaller than chlorine means it has one lesser shell, right? So essentially, it would definitely have stronger nuclear charge anyway. So is that your only reason for why the trend is it doesn't fit fluorine at all?
Because the effective nuclear charge in chlorine is larger.
Okay.
But then in bromine and iodine, they have the 3D orbitals and the 4D orbitals. They have the d orbitals, which increases shielding effect.
So going back to the argument again, you are saying that the effective nuclear charge is stronger in chlorine?
Yeah.
Why do you think that is? I mean, chlorine has one more shell than fluorine, so that shell alone itself is a lot. The n equal to 3 shell is definitely more shielding than n equal to 2 shell. So so I will cut you short there. The effective nuclear charge of a valence electron in chlorine is definitely stronger effective nuclear charge in fluorine than chlorine. Because look at ionization energy. You just talk about ionization energy being the effective nuclear charge getting weaker down the group because of more shells, because of increased shielding, and then suddenly you are going against what you said just now because you want to justify this trend. Do you get it? So you have just contradicted yourself. So there's always a kind of reason for this, and fluorine is one of those really weird ones. So there's nothing wrong with the ionization energy because that follows the effective nuclear charge and the usual shielding rule trend, right? So it can't be like it suddenly changed and then the electron affinity changed. No, 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 no. The value of the electron affinity is like that because there's something to do with the definition. So you define it as energy required enthalpy change when you add one mole of electrons to the one mole of gaseous atom, right?
Yep.
Yeah. Okay. So again, do you want to try again? Why do you think why do you think it's more exothermic for chlorine and less exothermic for fluorine? So the more exothermic it is, actually, the more favorable it is, right? So it's not as favored for fluorine than chlorine. It's not as energetically favored for fluorine than chlorine. Why is that?
Gosh. Uh,
So both of them have seven outer shell electrons. One is in the 2p subshell, and then the other one has five electrons in the 3p subshell. So for fluorine, you are filling in the 2p subshell, full set, right? For the chlorine, you are filling in the 3p subshell, full set, fully outer shell electrons, right? So so what makes you think the fluorine is less eager to gain the extra electron?
2p is smaller
Okay,
than
so
3p.
okay, so
So that means the unpaired electrons in one of the p orbitals for fluorine is less likely to accept an electron.
exactly, because it's actually down to the small size of the fluorine atom. Actually, fluorine is very small. If you think about atomic radius across a period, right? Fluorine is the smallest out of the 2p.
Yeah.
Yeah, because chlorine is the smallest out of the 3p, fluorine is the smallest out of the 2p. It's very small because of very strong effective nuclear charge. And then the electrons are in the 2p, and then you're trying to force another one into the 2p. Yes, it's very strong effective nuclear charge, but at the same time, there's also strong repulsion between the electrons in a tight space. Do you get it?
Yeah.
So everything is all about a balance of it's still favored, it still would like to get electron, but it's not as good as chlorine because there's repulsion in a tight space as well. Does that make sense to you?
Yeah, it does.
Okay, but think about it. Yeah, electron affinity is for one atom. Okay, then how about uh they don't ask about the bond length, but what can you tell me about the bond length and the bond energy? Essentially, part four.
Uh, the the bond length doesn't seem to affect the bond energy of fluorine because
Oh,
by right a shorter bond length would mean would require more energy to break the bond
why is that?
because electrons closer to the nucleus.
Okay, why is that? Why is the bond stronger then?
So if the bonding electrons is closer to the nucleus, it require more energy to separate the electron from the nucleus.
Oh, okay, cool. All right, okay. So now that you say it doesn't quite follow the trend for the fluorine, right? But you haven't really stated the obvious there. What is the trend?
The bond eh, bond length increases down the groove. So higher bond lengths, lower bond energy, except for fluorine.
Okay. Now you know what is the next question, right? Why is that? Why is the bond energy
Yeah,
abnormally low?
why is the bond?
Even though the bond is the shortest, it should have the strongest covalent bond. It is the strongest. It should be the strongest covalent bond because the bond is really short. Like you said, it should be really strong attraction between the bonding electrons and the two nuclei. Then why is the bond energy really low? I mean, the value is in front of you. These are experimental value.
Yeah, she required.
Any idea?
Not yet.
What did we talk about? What's so special about fluorine?
It's very small because of the
Okay,
high diffusion.
so we talk about the abnormally small size of fluorine, right? How do you think the small size can affect the bond energy in this case?
If It's which means that since it's very small, the
Mm-hmm.
bonding electrons would be affected by the electrons inside the fluorine atoms. So
But you see, yeah, when you form the covalent bond, the bonding electrons are fixed. It's in a fixed position. It's localized. It's not delocalized. It's localized in between the nuclei, and it should be a really strong bond, right? So
yeah,
here, in actuality, the reason for this abnormally low bond energy isn't to do with the bonding electron. It's to do with the non-bonding electrons. Think about what happens to the non-bonding electrons and how they will be like in a fluorine molecule versus in a chlorine molecule. So we talk about the small size of fluorine atom. So when you try to form a fluorine molecule, then the two atoms have to come really close together. Are you with me?
yeah. Chlorine.
Let's talk about fluorine. Let's talk about fluorine. So when you form the molecule, the size is really small. Yeah. So when the size is really small, so the bonding electrons are localized, but the non-bonding electrons they are kind of localized as well in each of the p subshell. But you see, like fluorine is really really small. So what do you think this non-bonding electron on each of the fluorine atom will do? So you got one fluorine atom and one fluorine atom, covalent bond. Yeah. So you got the non-bonding electrons. What do you think they would do in such a abnormally small fluorine atom? Each fluorine atom is really small, right?
Repel.
And
Repulsion
when that happens, which so the strength of repulsion, right? Do you think it's stronger in fluorine or chlorine?
in fluorine because they're all dense.
Because yeah, because they are so such small, and then you're having them in the 2p subshell, which is closer to the nucleus than in the 3p subshell, right?
Yeah.
So when they repel, so what do you think would happen to the bond? The bond strength. So on one hand, your bonding electrons want to bond together. But on the other hand, the non-bonding electrons, which are not bonding, they like to repel to each other because they want to stay further away from each other, right? So that would weaken the bond in a sense, and hence you get this abnormally low bond energy for fluorine. But
Yeah.
then you cannot change the size of the atom itself because the electrons are fixated. They are moving around in that fixed subshell at approximately the roughly the same distance, for n equal to 2 versus n equal to 3 is further away. So
Yeah.
therefore, your bond length is governed by the size of your atom. But your bond energy is to do with how strong they attract. But this strength of attraction, called covalent bond, it's kind of weakened a little bit by this repulsion of the non-bonding electron, which can happen, when you have like non-bonding electrons. But this is
Yeah.
not the case. This is not the case when you have no non-bonding electrons, such as in hydrogen. Hydrogen is like fluorine, but there's no such thing as extra non-bonding electron because hydrogen uses the only valence electron for bonding, right?
So it's very high, the bond energy.
Yeah, hydrogen bond energy is way higher. So I could have asked you to explain HH versus FF, right? The bond length is similar in size actually because fluorine is very small. Hydrogen is even smaller. So essentially, there's not much difference in the bond length, H2 and F2, but H2 is a lot stronger covalent bond than fluorine. And that's all down to the non-bonding electrons repelling each other due to the small size of the fluorine. Whereas that's not the case in hydrogen and not the case with chlorine, bromine, or iodine. Does it make sense?
Yeah, it does.
These are things that you should have learned from AS, yeah? Anyway, cool. Do you want to talk me through part 5?
Okay. The bond energy for fluorine is much higher. So
Really?
if
I thought the bond energy for fluorine is
in
lower than chlorine.
bond energy in carbon tetrafluoride.
Okay.
So that means it would be uh,
Did you scribble any notes for this?
Not really.
Okay. Why don't you think on your feet right now? We'll see how well you can think. And you should think before you speak so that you don't contradict yourself all the time. It's okay to make one or two mistakes along the way, but it's certainly not okay to have to be corrected throughout. Yeah, you could ask for guidance, but you can't be guided throughout the way because that's not how it works in a tutorial. So I can
Yeah.
give you a few ideas, then you should develop from there. So the idea here is really you have talked about the end product, the carbon tetrahalide. You have talked about the bond energy. You have talked about it's the highest in fluorine, and therefore you really want to form CF bond versus CCl versus CBr versus Ci. But
Yeah.
you have really talked on one side. You have talked about the forming the product, which is forming the CX bond. But in order to get there, what do you have to do? You have to react the elements. And the element all exists as diatomic molecule. So what must happen to the elements, the molecular halogens before they can react to form this CX form?
They must break by
Sorry, go on. You
the
need
bond
to,
must
yeah, okay.
the bond must break by homolytic fusion.
We are not necessarily talking about heterolytic or homolytic fission, really. I mean, don't care about it in such inorganic reactions. But to be honest, I mean, the bond must break essentially. If the halogen bond doesn't break, it's not going to react. So it has to break. So on one hand, you have talked about the product. So yes, that trend is clear. You are forming stronger bond by forming CF versus CCl versus CBr versus Ci. But in terms of breaking the bond, the reactants, what can you tell me? Which one is the easiest to break?
The fluorine bond.
No, that's not true. Do you have a look at the data itself? Which one has the lowest bond energy for the halogen?
Iod iodine.
Okay, you see that? So iodine is actually the weakest to break. Yeah, the easiest to break. Yeah,
Yeah.
okay. But then in terms of forming the carbon iodine bond, it's not so energetically favored as well, right? So we have talked a little bit about this energetics. It doesn't seem to follow a trend at all. Okay. Yes, fluorine is quite easy to break. Well, almost as easy as iodine, because the small size, the weak covalent bond, you can see the bond energy there. But then you're also forming much stronger carbon fluorine bond.
Yeah.
But then we're also talking about the ability of the halogens to oxidize something else. So its ability as oxidizing agent. Its ability as oxidizing agent means itself is being reduced. Yeah. So you're going from the molecular state, which is oxidation state zero, to become the tetrahalide, to become a halide, which is oxidation state minus one. So essentially, in terms of inorganic chemistry, it has to gain electron, right? It has to gain
Yeah.
electron. So if you draw up like the bond energy diagram, so the covalent bond has to break. When it break, it form gaseous atom. Then what happens to the atom? The atom has to gain an electrons in order to be reduced. In order to oxidize other thing, itself must be reduced. Itself has to gain electron. Yeah,
Yeah.
and then you can relate that weak bond energy of the fluorine because it's not as easy, sorry, it's not as difficult to break, and you also want to get to the F minus one state, and then you have a look at the electron affinity as well. So it's getting less and less energetically favored down the group as you can relate the electron affinity, the bond energy, as well as the bond energy of the halogen versus the bond energy of the resulting product as well. So there are a few things to talk about here really. So these are trends. I could I could give you a graph instead of numbers that will make your life easier, or it might not. But the most important thing is when you see numbers, the most important thing is you should visualize it as a trend. You should try and sketch out a trend. And then you should try and justify them. Is it atom or is it molecule? What is going on? Do not just focus on the product, focus on what happened from the reactor to the product. That is a chemical change. And when you want to talk about why a reaction favors something, you have to think about product, reactant to product. What happened to the reactor? What happened in forming the product? Yeah?
Yeah.
Okay?
So
Are you okay so far?
um
Hello?
yeah, wait. I think
You need to pick things up a little bit faster, yeah? Because like that's how it works in the tutorial. Like in a short time you have an interview, they will guide you a few things, and then the more you get slow down, the lesser they'll be able to assess you on your full ability. Yes, I don't
uh,
mean like talking really quickly or whatever, but you need to think quite rapidly on your feet. Otherwise, you'll be disadvantaged. That's the idea. Okay.
uh,
And a lot of these questions they come out of the blue. You can never really prepare one because they can ask you anything. That's why this whole Skype session is basically I throw a few curveball at you and see how you think. And so far you haven't really been doing that well. Okay, but let's keep going on. Shape of molecule. Are you okay with shape of molecule? These are AS topics again, right? Again, they'll ask very general question. Shape of molecule is a very popular one. But they won't ask you something which is quite common in school. They might start you off like that, such as BF3. So these are all the fluoride compounds, right? The fluorides of non-metals. These are non-metal fluorides. So what can you tell me about the shape of BF3?
should be planar because
Okay,
there's three bonding groups. The furthest they can get away from each other is if they arrange themselves in a planar formation.
okay, okay. What are the bond angles there? Because I would have asked you to draw for me, but like I'm currently recording this and I can't really see the video at the moment. But anyway, what can you tell me about the bond angle?
120 degrees.
Okay, when you talk about geometry, you should talk about the shape, the bond angles, those kind of things as well. Yeah, and a planar can be a square planar or trigonal planar. You should make yourself very clear. How about PF3?
Uh, Phosphorus has a lone pair, so that means there's four bonding groups.
When you did this, do you do it with a periodic table?
Uh, Not really.
Okay, you shouldn't refer to the periodic table because you won't have access to the periodic table during interview. Okay, you should definitely know the first 20 elements in order. Can you tell me the first 20 elements in order, please?
um, Hydrogen, helium, lithium, beryllium, boron,
What group is boron in?
group 3.
Okay, what's next? Next will be group 4, right?
It's
First 20 elements.
a
It's an element of life.
carbon. Yeah,
Gosh, you cannot
carbon,
forget that. Yeah. Group 14, that is the most important one. Anyway, so next up will be group 15.
which would be nitrogen, and then oxygen, and then uh, neon.
No,
Yeah.
oxygen is in group 16. You miss out the 17.
Oh
You
no,
see,
fluorine.
when you do this kind of predictable thing, any competent chemist should be able to visualize at least the first 20 elements. You've done chemistry for a few years now, you should be able to visualize where they are because when they ask you a compound or whatever out of nowhere, you won't have access to the periodic table, and then you will look a bit out of place if you start asking where is this, where is that from, because by right you would have known better. Yeah, okay. So neon is
Yeah.
the group 18 noble gas. After neon,
It's sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and then argon, and potassium. Wait, yeah, potassium, magnesium. Wait, no, strontium, I think.
That is calcium. So again, this group 2 chemistry, yeah? Okay, so what is above aluminium in the periodic table?
Above aluminum, boron,
What is below carbon?
silicon,
What is below oxygen?
sulfur,
What is below magnesium?
calcium,
Okay. What is above chlorine?
fluorine,
Fluorine, yeah. Okay, cool. All right. Now, how about PF3? What's the shape?
trigonal pyramidal,
Okay,
bond
go on. You should.
angle
Mm-hmm.
slightly less than 107
Okay. You should be able to tell me why. Why is that?
because the lone pairs is takes up more space than the bonding
Why is that?
because they are free to move in their orbital.
Yeah, so
So
do you know the idea of shape of molecules? It comes from a theory called valence shell electron pair repulsion theory, right? So you have stated about lone pair, but you haven't really invoked the idea of the theory yet. What does it say?
electrons try to go as far as possible away from each other.
Okay, but there are two different kind of electrons. You also have the bonding electrons and the non-bonding electrons. Bonding electron will be the bonding pairs. The non-bonding electron will be the lone pairs.
The non-bonding pair is the electrons are delocalized, but then the bonding electrons are fixed, so it takes up less space.
Uh, it's not ideal, sis. I'm sure you had learned this from AS. It's all about the non-bonding electrons on the phosphorus, yeah? It will repel with the bonding pair. The bonding electrons will repel with the bonding electron as well. But the lone pair and the bonding pair will repel more than the bonding
Both
pair of
pair.
electrons. Have you
Yeah,
learned that before?
yeah,
Oh, okay. So you shouldn't forget about those things. These are general thing which other people being interviewed, having done their AS, they will have been able to justify it very easily. It's got nothing to do with delocalized or whatever. By the way, the long pair is not delocalized at all. The long pair is still localized. We are not talking about when you say delocalized, it means that you can freely move between the p orbitals, but it doesn't. Okay, it's stay there on the phosphorus. It doesn't go into the fluorine at all. So therefore, it's not delocalized. You got to be careful with what you are saying verbally, because once it's out of your mouth, it's really hard to control whether you're talking about the right chemistry or not. Yeah, that's the
yeah,
thing about writing and talking. Once you once you blabber out something, you cannot take it back. And the more like, oh sorry, 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 not that, not that. Oh sorry, 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 not that, not that. You can't be caught out more than once or twice. Anyway,
yeah.
SF4. What can you tell me about SF4?
Should be square planar.
Okay, do you want to tell me why?
It has two unpaired electrons and four bonding pair electrons.
When you say four bonding pair and did you say two unpaired electrons? So there is one lone pair. So where would the lone pair be then?
Above the plane.
Okay. Can you? I'm gonna stop recording.